This is Chapter 3, Part 2 for EE160 in Section 310 right now, which is yet the third case study program in the textbook. The main thing about this new program that we're going to look at is nesting of the control structures and use of more data types. But before I go into use of more data types, I'm going to give you an overview of this. It does show up later in your textbook, but I think rather than introducing a data type here and there, I think it might be useful for you to get an overall picture of what these other data types are. So I made this presentation. So I called it somewhere between Chapter 2 and 3, or somewhere in maybe it's between Chapter 3 and Chapter 6. So more about data types and format specifiers and conversion specifiers. So really, for purposes of where we're at right now, there are about 5 data types that we can work with. There are really more than that, but it gets a little bit more complicated, and we aren't going to talk about them right now. But on a basic level, there are 5 types. There are integers, floats, that's where there's a fractional part. Doubles are a precision floating point value. Characters, and a void, which is a special purpose type that we will look at later. So those are basic types rather than some of the more complex data types that we'll cover later. So here's some examples. An int doesn't have a decimal point. A float can be expressed as exponential type notation. So speed of light, 2.99 times 10 to the 8th. You can express it that way in your program. Double is double precision. It's also a decimal point, fractional, and there's a character example. So just look for a moment at just the numeric data types. So there are basically 2 types of numeric types, floating points or integers. And keep in mind that C is what we call a very strongly typed language. Actually, all the C families are, so are C++ and C#. So you must declare your variable types with a specific type specifier, like we've been doing, and you have to be consistent with using it that way in your program. So of the floating point numbers, we have a few choices. We have a float type, a double type, and a long double type. But notice that double has twice as many bytes to represent the number as a float does. So that's why we call it a double precision. We aren't going to worry about long double right now, but we're going to compare, like float is 4 bytes and double is 8 bytes. Of the integer numeric data types, we have an int, which is 4 bytes, and int long is also 4 bytes. But there's also an int short, or short int, which is only 2 bytes. I haven't really covered all of the data types, but if you go to msdn.microsoft.com and you search for it, you can get all of the data types. So I've taken a few of them that are of interest to us right now. For example, an int is 4 bytes. And the range of values that an int can represent is over here on the rightmost column. A character, notice, is only 1 byte. It's actually when we talk about ASCII, how a character is stored in the computer, you will see it's only 1 byte. 1 byte is 0 to 255 bits, or you could represent it as a signed value. There's also a short int. It's only 2 bytes, so you can only represent numbers between these 2 values on the right. Look at the difference between float and double. So float and double allow you to represent fractions, but double, you can see, can represent a very much larger number than a float can. So those are kind of the difference. So floating point numbers represent both integer and non-integer, and as we said, we can express it in scientific notation or exponential notation. That's fine. Character data types are enclosed in single quotes, and I have letters, but keep in mind that a number can also be stored as a character, and we will later in the course see how that comes into play, actually very soon. Any of the character types are stored in memory as a binary value, and that encoding what binary value it's given is called the ASCII code. ASCII stands for American Standard for Information Interchange. Here's an example of ASCII. For example, the character, not number, the character 3 is stored with this ASCII value if you were to convert this binary base 2 number to an integer, it would be 51. So when you type a little a, it's stored in memory as, here it is, our bits, which is a binary number, but in decimal, which is our base 10 numbering system, this is a number 97. So when we use our printf statement, we need to have a format specifier. So for example, if our data type is an int, our format specifier would either be a %i or %d format specifier. And then there's some subtleties in here. The program that we're about to look at looks at an unsigned int, which the format specifier is a u. When we use our floating point numbers or our decimals, we use the %f. I used LF in an example in the previous YouTube for long float. %e gives it an exponential notation, and we'll talk about the rest as we need them. But this is a chart showing you. So here's an example. We know int, I'm declaring an integer variable called inches per foot with the identifiers inches per foot, and it's 12. So if I want to output inches per foot, I won't get an error if I say 5i, but the number 12 will be output. Here's the example. The example for the second line, I used d as the format specifier instead, and I put a 5 in front of it. So what that does is it says it gives me 5 places on your console output to display the answer. So 1, 2, 3, 4, 5. If I put a 0 in front of it like that, I can actually put zeros in front. So this is just a little bonus, more material about what the format specifiers do. And let me pop up this other thing real quick. That's not the program I want. It's this one. So this one actually might be quite useful for you in some of your homework problems. Maybe I'll capture that and stick it in the PowerPoint as well. So here's my use of the string specifier, so I can output blue. Here's an int, here's an int, here's an int, here's a floating point number. This is how you would make a hexadecimal number come out. You should try this program and see what the results will be. Or an octal number, or how unsigned int comes out, or what if I just wanted to print actually the % sign? This is how I would do it. Actually, maybe I'll go ahead and run this program. Let me pause for a minute and I'll run it and I'll show you what the results are. Okay, I'm back. So I compiled it and ran it. So I would study this example very carefully. For example, the float number, which is pi, I specified 3.2f. So 0.2 means I can only have 2 significant digits after the decimal point, and sure enough, I only print 3.14. When I print something in hexadecimal, which is a %x format specifier, the number 255 will print as in hex FF. 255 in octal, those are you who are taking my digital class, octal will be, it's a base 8 numbering system, will print as 377. This number, unsigned int 150, still prints as 150, and in this case I just wanted to print the % sign. It didn't matter that there was a 10 right there because I just printed the % sign. So this is an example very worthwhile studying, and I wanted just to kind of give you an overview of these format specifiers before going into the example problem that we're about to look at. So our example problem, our third case study problem that we're going to look at, in this case we are going to have some nested counters, or we're going to use nested control structures, I should say. So basically you're looking at the performance of a class of 10 students, and if the student passed an exam it's going to ask, did the student pass or not? And the user is going to enter a 1 for passed and a 2 for failed each time you're entering for a student. And in the end, the program is going to count how many passes there are and how many failures there are, and see if 80% of the students passed, then the instructor gets a bonus. So that's what the program has to do. So then we kind of look at it a little bit further. I'm looking at your textbook. Program has to process 10 results, so we're going to control that with a counter, with a loop. Anytime you say something that happens iteratively, it better be a loop. And then the user is going to enter 1, 2, either passed or failed. So we have to count how many times the user enters a 1 for passing and how many times the user enters a 2 for failing. So we need 2 counters. After the program has processed the result, well, we probably need 3 counters, 1 for the number of students total as well. After the program has processed all of these results, it must decide whether 8 students passed the exam, and then the professor is entitled to a bonus. Bonus? I don't get a bonus if more of you pass than not. So there's some examples of your textbook of what the pseudocode might look like. It's worthwhile to read through it. It's a good top-down way of processing and developing an algorithm. Finally, we get to the next level of refinement. So we have to do some initialization. Initialize the number of passes, initialize the number of failures, and initialize the students. And then it discusses inputting each one and what the program needs to do. So let's look at actually the program, and I'm going to point out the really important features of this program, what makes this program different. So once again, I got from the author's version, which has lots and lots of comments just for you. So we do our initialization of the variables that our program is using. And while the student, which is how many number of students are, while that's less than or equal to 10, then you're going to ask the user to enter a 1 for passing or a 2 for failing and store it in a place called result. Then here comes the test. If the result is a 1, then you're going to increment the passes counter. This is a counter incrementing the number of passing grades. Otherwise, if it's a failure, which would actually mean that the user entered a 2, then you're going to increment counting the number of failures. And we're going to talk about these counters incrementing up and down here shortly. So one or the two things will happen. If I were to do this more smartly, I would have also put a condition where the user entered something erroneous. Like, what if the user actually entered a 3? What is the program going to do? It will probably, my guess is that it will crash, and really for proper control of this program, we should have had a if, else, and the else should probably say you have entered an incorrect number or something like that. But anyway, and then you're going to count the total of number of students. After you're done, there's something not quite right here. Oh no, it is correct, because you're doing it for a known number of 10 students. Here's my while statement. Here's the closing curly brackets that I was looking for. Okay, so I have, in the end, I have a number of failures, I have a number of passes, and I have the number of students altogether. So I can print the number of passed. This time the author used an unsigned int, which is fine. You can print the number of failed. And then you can do one more test. If the number of passes is greater than 8, then bonus to instructor. So some more details. Section 3.11, assignment operators. Let's look at this little piece of code right here. We can say C gets assigned C plus 3. So what we have here is that C plus 3, whatever the value of C is, maybe I should have initialized it. C is going to get 3 added to it, and then the new value of C is going to get assigned to that value, or C is going to get assigned that new value. So we have C as a variable, the plus sign is an operator, and 3 is an expression. Alternatively, we could write it with this next line of code that's shown, where I have C plus equals 3. The plus equal sign is called an addition assignment operator. So it does exactly the same thing as the line before it does. As a matter of fact, there are a whole bunch of assignment operators that your textbook has. There is a plus equals, there is a minus equals, a times equals, and a divide equals, and there's even a modulus equals sign. So there's some kind of let me zoom in a little bit on this. There are some nice examples right here in your textbook, but the easiest way to test this is to put it in a little piece of code and print the results for yourself. But for example, E times equals 5 takes the value of E, which is presently 4, and so it's really the present value of E times 5, and then the E gets that new value. So 20 will get assigned to E. So they all work similarly on the assignment operators. It's kind of a shortcut notation. It's especially nice. Let's say I have I'm counting things. I could write counter equals counter plus 1, or I could say counter plus equals 1 and increment the counter by 1 that way. So it's a shortcut notation. But that brings us to the increment and decrement operators, which is another shortcut way of writing things that will become very useful. So because incrementing and decrementing by 1 is so common in looping structures, we have this additional increment and decrement operators that are a shortcut. So, but we have some subtleties with it. There is a pre-increment and pre-decrement, and there's also post-increment and post-decrement. So it is important the way that works, and I'll do a specific example. So we have a plus plus sign, and if I say plus plus A, then I'm going to increment A by 1 and then use the new value, assign the new value to A in the expression. But if I do A plus plus in the opposite order, I'm going to use the current value of A in the expression and then increment by 1, and then we have decrement by 1 too. But I think in order to see that, a specific example will help clarify it. So I'm going to give you an example. I repeated the example in your book on page, I guess it's on page 93. I like to do things for myself. It's nice to read through the book, but it really sinks in when you read them for yourself. So here I define integer x equals to 5. I printed x, so it's a 5. And then the next line I said x plus plus. So, but it's embedded in this print. So what's going to happen is it's going to print the current value of x and then increment it. So it did print the current value of x and then incremented it, and I can show that by the very next line. I print the value of x and it's 6. So now we can also look at this post increment structure. So the value of x is currently 5, and it says increment x and then print it. So I incremented x at 6 and then I printed it, and sure enough, when I show the value of x, it is indeed 6. So the last thing I'm going to cover in this chapter before I go look at my programming lab is this figure 314, showing the operators that we've encountered so far in the text. This is not all the operators that we're going to encounter. There's a whole nother set of logic operators that we haven't dealt with yet. But the order of precedence is important here as well. Like the last thing performed in a particular line of code will be the assignment, one of these assignment operators. But things like incrementing and decrementing a particular variable, that occurs before these other operations will occur. So and then this is the type of operator they are and their names. So these are unary because they only they don't operate on 2 variables. You can guess that these are not unary ones over here. And then we have a conditional statement and an assignment statement. So now let's take a look at a few of my programming lab examples to give you hints when you go through it. Although I haven't quite set up yet all of the ones that I'm going to assign to you. I don't think you need to do all of them at this point. So I'm going to go over here to my programming lab and go over, I think, a few of the examples. Oops, let's get rid of this. Sorry, waste your time for a moment. Okay, so here I am in my programming lab, and I want to go over a few of the examples from chapter 3 just to give you a heads up. So the if statements are pretty easy. If you read it very literally what they're asking for. So assign 10,000 to a variable bonus if the value of the variable goods sold is greater than 500,000. So if goods sold is greater than 500,000, bonus equals 10,000. So the if selection problems are very straightforward. So are the simple if-else. This is one I'm actually probably not going to give you. The simple if-else statements are also straightforward. I'm actually not going to give you that one because they made it more difficult than it needed to be. And then we can cascade if-elses. If your age is less than 18, the number of minors is incremented. So I've used the plus operator there. Else if the age is less than 65, the number of adults is incremented. And the final else is somebody who's not less than 18, not less than 65, so they must be over 65, so seniors is incremented. We have some examples of conditional expressions, but they tell you specifically to use the conditional operator. So if x is greater than or equal to 5, that's the test, right? Then if that's true, you're going to output x. If it's not true, you're going to output minus x. So there's the example. I hope you guys can read this. Let me make it bigger. There's the example of the conditional. Oh, I can't make that anymore. There's the example of what they want for a conditional operator. Some of them are a little tricky syntactually, but I believe that every single answer there is a one-liner. Okay. Counter-controlled. I might do a few of these examples. Remember the while loop, you have to initialize the loop before you go into it, do the test, and then if the test evaluates to true, you're going to do whatever. In this particular case, you're going to output 97 asterisks on a line, so there's no /new line in there. Those problems aren't too bad either. Again, read them very literally. And let's look at the Sentinel controlled ones. These get a little bit, probably a little bit more detailed. You might spend a little more time on them. I'm going to take some of these out because you'll spend all your time doing them. This particular example, write a loop that reads positive integers from a standard input. That means you're going to do a scanf statement, printing out those values that are greater than 100, and then terminating when you read an integer that is not positive. So your Sentinel value is maybe a -1, or anyway, it's something less than 0. Values should be separated by single spaces. So this problem is a little bit more tricky. You're going to read from the standard input some kind of a value. It's an integer, right? So I have a good scanf statement. And while the number that you read is greater than 0, what are you going to do? This is nested. If it's greater than 100, you're going to print the number. and then you're going to scan for the next number. Is that what it said to do? Let me check here. Yeah, you're going to print out only those numbers that are greater than 100. So if it's greater than 100, you're going to print it out. Otherwise, you're going to scan and get the next number until at such time you don't get a positive value. So those are good. That's a good example. Let's look at another one. Write a floating point literal. Oh, that's so trivial. Let's look at some declarations. These are also rather trivial, even if you, let's see how it does down at the bottom. It's still, they're still trivial to answer. So you'll get most of those problems. And oh my gosh, they went back to an exchange thing. Casting is important. All of the section on assignment operators, I think they're all one-line type answers. Just read carefully what they're asking for. Don't misspell, don't mistype your words. All of the increment, decrement problems are also straightforward one-liners. Read it carefully, answer it precisely. And I am not giving you the programming projects because I give you a specific programming example. Anyway, please join the Google Hangouts if you have questions. I'm very happy to help you with questions. And have a good week, everybody. Join the Hangout. Bye for now.